Ladies and gentlemen, if I could ask you to take your seats. Thank you very much indeed for being very punctual. If this were a flight, we would be taking off more or less on time. So thank you very much indeed. I hope you enjoyed your refreshments. Of course, we're here tonight to celebrate and to mark the handover of the technical design report for the ILC. And it is with great pleasure that I welcome here with me Professor Brian Cox. Now, you are also known as the rock star of the physics world. How does it feel to be called that?
Horrific.
Horrific, yes. I thought it right. But you're also called an inspiration, which must be much nicer as a description, especially to youngsters. But generally to the general public, making particle physics accessible to non-particle physicists.
I mean, I would echo what was said earlier, actually, about we talked about the spin-offs of particle physics, technological, economic, but also, I think Brian Foster mentioned the inspirational impact of particle physics. And we've certainly seen in the UK an upswing in applications to universities to do physics. And part of that, at least, social scientists will argue like mad because they haven't done the research yet, but it's widely accepted part of it has been the LHC, huge profile.
Yeah, it's been described as the new NASA, isn't it, because of that ability to inspire.
So I think we underestimate that.
And now comes the ILC. I was going to ask you, I remember quite a few years ago now, watching a talk of yours full of excitement, looking ahead to what we might expect from the LHC. So how do you feel now as the era of the ILC is, we hope, dawning?
Well, I'm going to describe in the talk, actually, I think thinking about what to say. I will say, actually, that this is one of the most nerve-wracking public talks I've ever given, because although it is a public talk and it's on the web, everybody in here knows at least as much, and significantly more in many cases, than I do about particle physics, so it's an interesting thing to do. But what I think you realise when you look back in order to give a public talk and to communicate what we've done is the sheer level of achievement of both the theory and the experiment. And that's really what I want to focus on tonight. It's when you look back on it and you look at it in detail, what has been done, it's quite remarkable. It's almost unbelievable.
Well, I hand over to you now. Of course, we all want to see you as one of us, whether it's a particle physicist or whether it's CERN. And I'm supposed to pass on the message they'd like to see you here more often here at CERN. Or whether I say one of us as a BBC journalist as well, because you're very much with us. But over to you now.
Thank you. Thanks. Well, I thought I'd start just very briefly as I suppose, a little matter of interest, a bit of fun, of showing this picture, which was released just a couple of weeks ago. We're going to talk, of course, we've been talking about the smallest objects that we know of in the universe. It's nice to just look at the biggest very briefly. This picture is thought to be the largest object in the known universe. It's called a large quasar group. It was discovered from the data in the Sloan Digital Sky Survey and published this year. And this line of quasars, so active galaxies, which are a redshift of about 1.4, so it's certainly, you're looking at galaxies that were around when the universe was way less than half its current size. This thing is 4 billion light years in extent. So it's thought that you're looking at a structure, a gravitationally bound structure of active galaxies way back in the early universe that is so big that it breaks the cosmological principle, if this is right. So the cosmological principle is that the universe is homogeneous and isotropic, so on large scales it's smooth. This structure is too big for that principle. Now, whether it turns out that this data survives scrutiny is another matter, but at the moment, the claim is this is the largest structure in the universe, 4 billion light years across. You extend that, by the way, over the entire sky. It's talking about these scales of galaxies. And I think often, as I said, when I look back on particle physics in order to give public talks and talk about it, you see the hubristic nature of what we do when you think about it for a moment. Because you look at the observable universe, which is the piece of the universe and beyond, indeed, that we are claiming to understand and are indeed understanding in detail, and you realize that maps like this show you there are 350 billion large galaxies in the observable universe, which is 90 billion light years across, and we claim to understand how all that interacts, what it's made of, and indeed where it came from. And I think the size of our quest, the almost hubristic nature, becomes quite obvious. I just say that, just to set the scale, that's the billion light year ruler. I mean, the numbers are really quite ridiculous. The universe is big, I suppose, is what I'm trying to say. As well as understanding and mapping the size and scale of it, we understand, of course, in detail, in some great detail, the evolution of it. From very close to the Big Bang. The fact that we can even talk about numbers like 10 to the minus 43 seconds after the Big Bang is remarkable. Of course, that number comes from the Planck scale, which comes from the weakness of gravity. There are 4 forces that we know of in the universe. Gravity is by far the weakest. One of the great mysteries is why gravity is so weak. And that leads through to some of the problems I'm going to mention later, in particular the hierarchy problem that you heard who mentioned it earlier. Anyway, mentioned earlier. So we talk about numbers like that. We then have the beginnings of experimental data when we start to talk about the time period from 10 to the minus 36 to of order 10 to the minus 32 seconds. That's the period when we think the universe went through an exponential period of expansion, inflation, increased in size by a factor of 10 to the 78. In the blink of, well, less than the blink of an eye. The reason that I say we have experimental data in principle is that certainly the measurements of the cosmic microwave background fit in with that theoretical statement, the idea that that's the way that physics was. There was that exponential expansion back then. Certainly not proven by any sense, and the mechanism, of course, is not understood. But the fact that we have a window now with precision cosmology for the first time on those eras is, I find, quite remarkable. Moving onwards then, at some point after that, we get electroweak symmetry breaking, which is the thing I'm going to concentrate on most in this talk. It's, of course, as you've heard, really, I suppose, the reason for the Large Hadron Collider, or one of the main reasons for building this machine, and also the reasons for building the ILC. What was it that caused that symmetry breaking? When did it happen? What are the details of that symmetry breaking? But, of course, then, when you move to 10 to the minus 10 seconds, a billionth of a second after the Big Bang or so, then we're in firm experimental territory. That absolutely is the energy range of the LHC and the ILC. Moving onwards, so we have a very firm, I think that's one of those things that when you think about it for a moment is quite remarkable, that we have experimental data that tells us about the universe, the physics of the universe as it was less than a billionth of a second after the Big Bang. Then we move on to nucleosynthesis, the fact that we can calculate with high precision the ratios of hydrogen, helium, in particular deuterium, lithium in the early universe, which gives us a very serious constraints on the physics of the early universe. I think, again, remarkable. And then we move on, and the rest is astronomy, so I won't bother with that. No, we can leave that with it. So it's worthwhile just looking back at where we are and how we got there. In Abraham Peiss' great book, the best book, I think, in the history of particle physics, Inward Bound, he talks about the period of time from around 1896 through to the discovery of the W and Z here at CERN as being a completely transformative era in human knowledge. He chooses 1896 because that's when Röntgen first discovered X-rays. Shortly after, and serendipitously actually, Becquerel, in looking for X-rays from uranium salts, discovers radioactivity. And even at that time, in 1896, there's a wonderful quote I found from Poincaré, actually. He wrote a review article in 1897. This is 1 year after the discovery of radioactivity, a couple of years after the discovery of X-rays. He said in his review article, "One can think today that it will open for us an access to a new world which no one has suspected." Even in 1897, the importance of the beginnings of particle physics, the discovery of radioactivity, was recognized. And in fact, if you then look back from the point of view of the 1920s, this is an era, 20 years, part of a scientific lifetime, when we get very quickly radioactivity, we get quantum theory, we get relativity, the foundations of modern physics, Noether's theorem that I'll mention a little bit later. And I found another remarkable quote, actually, from Ernest Rutherford, from Peiss' book. It's a wonderful book if you haven't read it. Looking back in 1924. So this is really, 20, 25 years after the beginnings of modern particle physics. Rutherford wrote, "The year 1896 marked the beginning of what has been aptly termed the heroic age of physical science. Never before in the history of physics has there been witnessed such a period of intense activity when discoveries of fundamental importance have followed one another with such bewildering rapidity." That's looking back at that period, the turn of the 20th century. I actually genuinely think, and I wonder whether many of us do, that we're living through the beginnings of such a period now. As we've seen in the previous talks, and I'll mention in this talk, the level of precision with which we understand the universe at some level is quite remarkable. But also the number of experimental results now that are beginning to say that there needs to be a real shift in our understanding are also building up one after the other. We've seen, of course, dark matter. We're looking at things like the hierarchy problem, the G-2 of the muon. All those results seem to point, dark energy, of course, all those results seem to point to a revolution in our understanding of the universe because of the experimental data that we are gathering in both cosmology on the largest scales and in particle physics at the smallest scales. And that's why, actually, I just wanted to, I put up that little picture behind the standard model because that's a Geissler tube, which was the driving force behind the discoveries of X-rays and of then onwards through the 20th century. It was also something called the Ruhmkorff coil, which was the way of getting high energies into vacuum tubes. And I think it is worth noting that even then, back all those years ago, it was technology, it was engineering developments that led to the advances and the discoveries in particle physics, just as it is today. It's really not changed. You look at the ILC, and it's basically that. Isn't it? It's basically a big vacuum tube with a bit of energy stuffed into it, essentially, which is what it always was then. Actually, I reminded again, I picked up a few quotes. I quite like quotes. There's a wonderful quote in the TDR, in the design report, actually, from Freeman Dyson, who says, "New directions in science are launched by new tools, much more often than by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained." Of course, you saw in the previous talk about the technological spin-offs of particle physics. Of course, X-rays, the beginnings of particle physics, tremendously useful. So, but I was thinking all the way through that talk of a quote by Feynman. He said, "Physics is like sex. Sure, it has some practical results, but that's not why we do it." I think it's... Anyway, so we look at the constituents. We're talking about the constituents of the universe as we've discovered them. Of course, this is the standard model that's been shown many times. Again, a 20th century discovery, apart from the electron, just before the turn of the 20th century. Every one of these particles has been pieced together, has been discovered almost, actually, within one human lifetime. The photon comes after the electron, and I just wanted to tell you a little story about that. I was looking through the discovery of these things. I thought what might be interesting to say. The level of skepticism with which some of these discoveries was greeted was great, even back in 1910, 1920. And I found a wonderful reference to something Planck wrote in 1913. Do you remember Planck triggered in many ways with his blackbody radiation spectrum, the explanation of it, Einstein to propose the photon. It was Einstein who first proposed it as a quantum of the electromagnetic field. Planck never liked that. And in 1913, Planck wrote, he wrote a reference, actually, to get Einstein into the Prussian Academy of Sciences. You imagine that it's difficult to get into the Prussian Academy of Sciences, even for Einstein, in 1913. And Planck wrote this is the level of skepticism. He said, "In sum, one can say that there is hardly one among the great problems in which modern physics is so rich, to which Einstein has not made a remarkable contribution. That he may sometimes have missed the target in his speculations, as, for example, in his hypothesis of light quanta, cannot really be held against him." Which I think was Planck in 1913. So, Anyway, onwards we go. So that's the standard model of particle physics sat there. And what I really want to do through the main part of this talk is to talk about the standard model, because I think that the level of precision of the theory and the precision to which it's been tested really does tell us something quite remarkable. It is surely the crowning glory, the most accurate piece of 20th century physics, without a doubt. If you look at our picture of the universe, I've described we found all these particles now, we've looked out into cosmology, we have Einstein's theory of general relativity, which sits up there, but the rest of it is contained within the standard model. Now, sometimes when I give public talks and I put that little equation up down there, the standard model Lagrangian, and I say that it's a very simple piece of mathematics, almost always people laugh. When actually, if you think that that does contain everything we know at the fundamental level about everything in the universe other than the theory of gravity, it's a remarkable achievement. And what I thought I'd try to do, and I've never tried to do this before, so it might go completely or horribly wrong, is to try and explain why, in the simplest way that I can, that equation got written down. Because what it contains are, essentially, is every idea, every fundamental idea in 20th century physics. It certainly contains, of course, relativity and quantum mechanics. It contains Noether's theorem. It contains the rich connection between symmetries and conservation laws. It contains spontaneous symmetry breaking, which is a separate idea to gauge symmetry, which it also contains. So really, what you're looking at there, I think, what we are looking at, is the culmination of the experiments, the great experiments from Becquerel and Röntgen all the way to the present day, and virtually every development in modern theoretical physics over 100 years. So I thought, how would I explain that? Well, essentially, as you all know in this room, but out there on the internet, people might not be so familiar with these concepts. In physics, we have the idea of a field. The simplest field I can imagine is the temperature in this room. You could represent the temperature in this room as a single number at every point. It might be 20 degrees over there, 21 degrees over there, 19 degrees near the door. That's a field, that array of numbers. But also, in physics, we have more complicated fields. A good example will be the magnetic field, which has both a direction and a magnitude at every point in space. And then there are fields, and these are the ones that I want to talk about, that have some kind of internal property. One of the most simple, the wave function of quantum mechanics, is a field that has, you can represent as a clock face at every point. A complex number, but imagine it, a little clock face at every point. And what we're interested in is the direction of the clock hand, and we're interested in the length of the clock hand. Now, in standard quantum theory, it turns out that the squared length of the clock hand tells you the probability to find a particle at a point. And to a large extent, when you're not doing calculations, the time on the clock makes no difference. So one of the key ideas in physics, in particle physics, is you look for what's called, I've mentioned them before, symmetries. You look for things you can do to the fields that leave the equations that describe the physics of the situation unchanged. In this case, I want to think about moving the clock hands around. Now, I'm going to put some mathematics up, which will be familiar, I think, to most people in the room, but it's usually considered to be scary. Now, I'm not doing this to show how complicated the mathematics is. I really want to bring out this idea that the standard model is intricate and beautiful and genuinely surprising in the way that it can predict the real world, the way that the mathematics works. Probably the best example of what Eugene Wigner called the unreasonable effectiveness of mathematics in the physical sciences. In many ways, one of the great mysteries. So the idea is this. This equation here, which you either recognize or it will strike fear into you, is called a Lagrangian. It's basically the Newton's laws of a particle, of a field. And what it's describing is the way that a field behaves. Now, what you can do, and what was asked way back in the 1920s, actually, was, well, what are the symmetries of this equation? What I really mean is, what can I do to these fields in order to leave this equation unchanged. Now, even if you know a bit of calculus, you might be able to see that if I write down the little clock faces for these objects here, these fields, and turn them all in exactly the same way, then this equation remains unchanged. That's called, in the technical language, a global gauge invariance. But basically all it means is that I found some property of these fields that are describing particles that I can move around and leave the equations unchanged. Now, I mentioned earlier, actually, Noether's theorem, a great piece of theoretical physics, which connects things like that, it's called a symmetry, to conservation laws. If you find something you can do to an equation that leaves that equation unchanged, then we know that that relates to some symmetry of nature. There's one translational invariance, is a very simple one. If you move the laws of physics around over here and over here, then they stay the same. If that's true, momentum is conserved. If you've got a rotational invariance of the laws of physics, so they're the same as you move around, angular momentum is conserved. This symmetry turns out to conserve electric charge in the right way, which is interesting. And that was noticed back in the 1920s. And so the question was asked, given that electric charge is conserved at a point, it's not that you can create a load of charge over here and destroy a load over here instantaneously. That's not the way things work. What really happens is charge is conserved everywhere you look at it. Could it be the case that I can get my little clock faces and twist them around, but twist them around by different amounts? Everywhere, right across the universe. I'll turn that one by 10 minutes, and that one by 5 minutes, and that one by 6 minutes. Could it be that the laws of physics can be invariant under that? It's a very strict and stringent idea. This is called a local gauge invariance. And in fact, it turns out that this equation that I wrote down there is not. And it's not surprising, because I'm twisting these little clocks at different places, at every place, all over the place. What was noticed, though, is you can fix the equation up. And this is the key point. This is the point I want to make. It's a deep point. It lies at the heart of the standard model. The point is, I can fix this equation, and I can do it, really, in one way, which is this. And when I do that in public talks, everybody screams as well. But it's actually quite easy to see, in a sense, what's happened, even if you know a bit of calculus and know nothing else. What you have to do, this is the prescription, is you have to introduce a new field, which is new particles, essentially. And the way that field changes when I turn all the clock faces is absolutely laid down by the prescription that I want to move all those clock faces and keep the equations the same. There's no freedom at all in the way that I write that down. And you can almost see what's happened, actually. If you know any maths at all, you can see that I'm going to stick that in there, and this is a derivative, so I'm going to pull these things down, and I'm going to have derivatives of these things, and they're going to mess up the invariance of this equation. And what I've done there is stick something else in that gives me derivatives of those things which are going to cancel them out. It seems like a completely random thing to do. Turns out, though, it is not random. It is a profoundly interesting and important thing to do, because the form of this field, as I said, is forced by that rather abstract and bizarre requirement, but it turns out that what I write down to fix it up so my strange local gauge invariance is respected is the equation for the theory of electromagnetism, forced. So what I did, what I had to do, what I was forced to do, is to introduce a photon into this theory, the carrier of the electromagnetic force. And this is deep and interesting and quite profound. You can get into the philosophy of it. There are many ways of looking at this. I introduced it by talking about local charge conservation. But one way of looking at what happens is, given my predilection for these beautiful symmetries, given my idea that I want to twiddle everything around at different places in the universe and I want everything to stay the same, then I have to introduce these things, these photons, to move around and fix up the mess that I've made. That's one way of looking at it. So this is a plank of the standard model. And actually, if you flip back to that equation, the standard model Lagrangian that looks such a mess, then you can immediately see the structure of the first two lines have been generated from this kind of idea. That's the one that I just showed, the simpler version. You see these structures here, these photons that have been introduced, and you see the same kind of structures here and here and here. They're more complicated because the symmetries, the little rotations that I want to do are more complicated. They're not quite as simple as clock faces, but actually you can see the structure. So that's the first deep bit, I think, of the standard model. The second deep bit, which goes together, is something called symmetry breaking, spontaneous symmetry breaking. Again, a terribly big word. But what it really means is that spontaneous symmetry breaking, this idea, occurs. It occurs when the ground state of a theory doesn't share all the symmetries of the theory. Now that sounds, again, rather esoteric if you've never met the idea before. Fortunately, there's a very simple mechanical system that we're all familiar with that exhibits this property. It's a ferromagnet, a fridge magnet. See, the way a ferromagnet works is that all the electron spins, a property which determines how atoms behave in magnetic fields, above a certain temperature are randomly orientated. Magnetism occurs when they all line up. And what you find in that ferromagnetic system is that, as I said, at a high temperature, all the spins point in different directions. As you cool it down, it becomes energetically favorable for them to line up. In other words, it's a lower energy state of the system if all those spins line up into one place. Now, you can see that top diagram there that I've drawn, that's no longer symmetric. The equations that describe the way ferromagnet works are completely symmetric. All these spins come in all different positions. You'll find the equations have a rotational symmetry. But if you cool it down, then the actual physical system doesn't. The symmetry has been broken. And it's been broken in such a way that all those spins line up, and that's why you get a magnet that you can stick on your fridge. There's also another interesting little bit, which is a bit further on. But if you look at this little diagram here, then this represents little waves moving through the magnet. It turns out that because the interactions between the spins in the ferromagnet are very local, very short range, then you can get waves that move through the magnet, or spin waves, that really have extremely low energy. There's no resistance to their flow through the ferromagnet because there are no long-range interactions. Those are called Goldstone bosons, and they've been the bane of physicists' lives all the way through to the 1960s. I want to mention that a little bit more, so let me carry on with the standard model, and I'll come back to it. So I've written down my equation again, my Newton's laws of particle physics, the simple version. Remember, there's my photon that popped in through gauge invariance, and all I've done is I've added two terms. This term is, and we're going to see these appear a little bit later on, is what's called a mass term. So it basically gives a mass to these fields. And this term here is what's called the self-interaction term. So it's a term that describes how those fields, those particles, could interact together. That's fine, and that's a perfectly valid equation. But now you can do something extremely strange. And this is the second part. And I want it to sound strange, because I think it is. It's a very odd thing to do. What you can say is, well, what happens if I let my mass squared here, this is the physical mass of a particle, what happens if I make it negative? What happens if I make the mass squared negative? That's strange. You end up with an imaginary mass if you take the square root of it. It seems like a meaningless thing to do. What you do, if you do that, is you convert this not into something that has a very simple explanation, but into a potential. Into a potential in the sense that, well, it looks like this. There's a maximum of the potential and a minimum of the potential. And if you know a bit of calculus, again, you could do a bit of calculus on something that looks like that, and you could find that the potential has this shape. When you make this rather strange choice, arbitrary almost, I want to let the mass squared be negative. This is a very interesting thing, because essentially what you've got here is symmetry breaking, in the sense that if you look for the minimum value of the energy, then it's not when the fields are zero. The fields are zero here, 0, 0 on this axis. But making this rather strange choice, you find out that the zero, the lowest energy, the vacuum, if you like, sits over here, where those fields are non-zero. This is why you often hear of the Higgs described as a condensate. Essentially, what you're saying is that empty space isn't empty. Given this prescription, you get a situation where the lowest energy you can possibly have in an empty place is when it's full of particles. It's full of fields. The fields are non-zero. Now, what you can do, so you can observe that and think, well, that's kind of interesting. It's a bit like a ferromagnet. The vacuum is over here. So you can transform. You can say, I'm going to move this whole theory into that vacuum. I'm going to shift it. This is written here, where the lowest energy state is, well, it's not the vacuum. The vacuum's over here, so I'll shift it. And I shift it mathematically like this. And the reason that I'm doing that, again, is not to confuse everybody. I don't want to drown in mathematics. But I hope that you can just see, very simply, that if I make this substitution, so I move my whole theory into this vacuum, the lowest energy state, because I made this funny thing with the potential, then this term here multiplies that, and I end up with this bit. And I end up with some other bits as well. This bit now looks like a mass term for the photons. So what's happened is that by doing this little, I don't know, little trick almost with the potential, then what happens is that very naturally I get a mass for the photons. Now that is extremely important because we know from experiments all the way back to the 1930s, 1940s, 1950s, that one force in particular, of the four fundamental forces of nature, the weak nuclear force, has photons that have mass. They're called the W and Z particles. They're extremely heavy, actually. Now, we also know that if you write down a theory and put masses in for photons by hand, the gauge invariance is broken. This wonderful thing that I showed on the previous slide that generated all this tremendous structure, and it's an incredibly exciting thing when it was noticed, that is broken if you put mass terms in for the photons. But if you generate them in this way, by doing this rather strange thing with a potential that seems very arbitrary, then a mass term magically appears. This is a theory now with massive photons like the W and Z particles, which were observed to be massive. Also, sort of for free, you get another mass term here sitting in front of this field. This is the Higgs particle. This is a massive scalar particle. And very interestingly, those Goldstone bosons I mentioned, those spin waves that go through the ferromagnet, those horrible massless scalar things that we don't want in the theory, disappear. So the upshot of that, I know it perhaps is a rather ambitious thing to do, to try and explain that in about 10 minutes, but what I want to get across is that there are several fundamental interesting ideas here. There's local gauge invariance, this wonderful prescription that by looking for symmetries and seeing if you can build a theory that respects those symmetries, you can get conserved charges and you can also get photons. You build the structure of theories like electromagnetism and indeed the strong and weak nuclear force. And then, by this rather odd mechanism of spontaneous symmetry breaking, you can generate masses for those photons, and you can end up with this extra prediction for this thing which turns out to be the Higgs particle, is, I think, quite remarkable. And I've put those two theories next to each other so you can see something else, which I think is very remarkable, and which leads on to the point of the linear collider, the International Linear Collider. What do you want to do with it? If you look at this theory, so I explained very quickly, but I hope with some kind of intelligibility, how these terms got into the theory. This thing here, this A, if I flip back there, you see that that's to do with the shape of this potential is to do with that funny imaginary mass, and it's to do with the self-coupling term, the way that I said that those particles I've just introduced talk to each other, the strength with which they talk to each other. That's this thing A. It's often called the Higgs vacuum expectation value. That sits there in front of the masses of these photons, as does the so-called gauge coupling, so the thing that I put in to respect the local gauge symmetry. So the mass of these things is mixed up with that potential that I invented and the interaction itself, which was generated by those symmetries. And again, if you look at the Higgs particle, its mass depends on the shape of that potential. and it depends, well, completely actually, on the shape of that potential. You look at the Standard Model and you see it again. You see that we have these couplings here. This one, and this one. These things feed through. If you measure processes that the Standard Model predicts, then you get predictions for the masses of the photons, not surprisingly, because the whole thing is a complex web of interdependencies, depending on all these ideas, sweeping back through 100 years of physics. And it's quite remarkable. You can extract the predictions. These are predictions that were made back in 1981, before, in this case, the W and Z particles were discovered. They were made using the Standard Model. You see that the mass of the W is related to this gauge coupling, as it were, this G, the Higgs vacuum excitation value. The mass of the Z particle is related to these as well. You can see them up there in this equation. You know where they came from. You can measure some of these parameters by looking at seemingly unrelated processes. In this case, primarily neutrinos bouncing off electrons, and you come up with a prediction. This is one that I found in the literature in 1981, before those particles had been discovered, predicted by the Standard Model with all those things that we put into it. And if you look at the precision measurements, the highest precision measurements of those masses today, you see that they are, first of all, astonishingly precisely measured, but secondly, in broad agreement with these predictions that were made over 30 years ago. So I think this is quite a remarkable state of affairs. What I hope you got from my quick description of the Standard Model, even if you thought it was mind-numbing and you didn't understand what I was talking about, at least I hope you got the fact that there are some fundamental ideas that went into the structure. They are all important parts, necessary parts of the structure of that theory, and they predict real things. That whole mess of ideas predicts real things that exist in the world, and it predicts them correctly. And it also predicts the existence of a Higgs particle. Now, how much time have I got left? Not much. Right, I better get a move on. We come to the Large Hadron Collider. I don't need to tell this story. Wonderful machine. What I always say about this thing, I think it's a remarkable thing, is that we have 88 countries around the world, I think, at the last count, collaborating, building the most complex machine ever built. It accelerates protons to 99.999999% the speed of light, collides them together. Tremendous engineering achievement. As I mentioned, it's one of the most important points, I think, of this talk, that engineering matters. We build it, we look at that theory, which is built on 100 years of theoretical physics and experimental observation. We turn it on. This is what the Daily Mail reported in the UK. James Gillis didn't help by saying that the planet hasn't been destroyed yet. But anyway, if James is here, probably yet would have been a nice stuff. Gizmodo was my favorite response to that, actually. CERN to morons, Large Hadron Collider won't destroy Earth, morons. And then if you can't read, they drew a diagram saying, turn it on, Bob. And it says, no. Anyway, there we are. So we turned it on. Our giant detectors detected Higgs bosons. And I thought at the end of it, when Peter Higgs said it's very nice to be right sometimes, was the understatement of the 21st century, given what I've said about the tremendous achievement. And of course, we've measured the Higgs mass now, 125.5. This is the latest Atlas result from the conferences. So relatively the beginnings of a high precision measurement of the Higgs mass. Now, just in the last couple of minutes, really, how long have I got left? A couple of minutes. In the last couple of minutes. So the first point I want to make is that there are many unanswered questions, although that's a triumph, the Standard Model. The unanswered questions are many. One is why we have 3 generations. I don't think we have any idea why we have 3 generations, where we have that structure of 12 particles when it appears you only need 4 to build a universe. Very importantly, and perhaps more within the International Linear Collider's remit, we have several so-called hierarchy problems. One of the great mysteries is the spread in masses. You see that the neutrinos, which we now have masses in the, 10 to the minus 12, 10 to the minus 10 GeV range, what is that? About well, 14 orders of magnitude or so, less massive than the top quark. Yet in the standard model, the basic standard model, they share the same mass generation mechanism. That can't be true. And there are theories, well, it could be true, but it's unlikely. There are theories that say how these things can get their mass, so-called seesaw mechanisms, etc. So there's the problem of the mass hierarchy. There's also the problem, which was mentioned before, about the top quark, which seems anomalously heavy, very close in mass to the Higgs up here. Why is that? Is that a coincidence? There's also a hierarchy problem that's related all the way back to the strength of gravity that I mentioned at the start of the talk. The point is that we believe in our theory. The standard model works, as I've tried to show. It's a magnificent, high-precision, superbly predicted achievement. So you can ask it things like what happens to the Higgs mass in the presence of what we call loop corrections. The standard model allows for the Higgs to change into a top quark and an anti-top quark and back into a Higgs again. And not surprisingly, these corrections affect the mass. What you find is that those corrections go quadratically, so as something squared, where that something is the scale of new physics. Now, new physics, in this case, if we consider the standard model to be valid all the way up to the Planck scale, all the way back to 10 to the minus 42 seconds after the universe began, let's say, this is an extremely big number indeed. You're talking about, what, 10 to the 38, something like that. So that looks odd. You've got corrections, naively, which seem to drive the mass of the Higgs particle up almost through the roof to astronomically high levels. Why does that not happen? What is it that protects that? There have been several papers over the last few days that have been speculative. One of the candidates, though, for protecting that is something called supersymmetry, which I'll mention I've got to whiz through because I've kind of taken too much time explaining mathematics. These ideas come together when you start looking at precision cosmology. I want to mention very quickly dark matter, one of the great mysteries. You see pictures like this, which are pictures where the blue areas are a mass distribution inferred from gravitational lensing, and the red areas are glowing gas. This is a galaxy collision, a collision of 4 galaxy superclusters, actually, where you see there's a lot more mass in the universe than can be seen in the gas and the stars. Measurements, many measurements that suggest that there's something else in the universe, 5 times as much as there is the standard model particles that we know of, dark matter. There are also these precision measurements of the cosmic microwave background. This is the first light emitted in the universe when it became transparent 380,000 years after the Big Bang. You can see that the cosmologists too have models. I just want to flash this up. It's a way of decomposing that picture into a graph that you can compare with theory. The standard cosmological model, is that green line, and the red dots are the precision data, the measurements of the cosmic microwave background. You see absolutely supreme agreement, but the agreement requires that we have this composition of the universe, which to a particle physicist doesn't look particularly like agreement, because everything that we study turns out to be 4.9% of the universe. 26.8% turns out to be, in these models, dark matter, a new kind of particle, almost certainly. 68.3% dark energy, something that's taken up in expanding the universe at an ever-accelerating rate that particle physicists have really no idea at all about. So the challenge from the cosmological precision data is for particle physics to explain most of the universe, if you take the data at face value. One of the great areas that the ILC will search for, new particles beyond the standard model. I just mentioned supersymmetry. It was mentioned before. The idea is that we have partners of all the standard model particles. What that does for you is it essentially cancels out, in a very high precision way, these loops that drive the Higgs mass to astronomical levels. Essentially, if these particles were the same mass as these, there would be no corrections at all to the Higgs mass. Some people take that as evidence that these particles should be just around the corner. If they are, the ILC finds them. But I think to finish, what I wanted to do in this talk really was to try and show the level of precision that we've achieved. The Standard Model is an incredible piece of work, using virtually every tool in the theoretical physicist's armory from the last 100 years. It works, but the unanswered questions, the precision measurements now are needed to map, in particular, that Higgs potential out. It sounds remarkable. We as far as we can tell, it's correct. We've got as you saw before now, that the level of precision that you need to start seeing deviations from the Standard Model may well be beyond the reach of the LHC. I think that's the key point about the linear collider. It seems to me that we should be entering a new age of precision measurements on this entirely new sector of a theory that's been around and confirmed spectacularly here this year. And I just want to finish with a comment. Again, I made one comment about the usefulness of physics. The first question we get asked as journalists, and I get asked all the time, can we afford it? Can we do these things? I think particle physics is clearly the main line of physics, which, as we saw, has generated virtually every medical treatment you can imagine and onwards, and energy sources for the future. But I just want to read one more quote to you, which I think is quite wonderful, because it was written in 1799 in response to a feeling that the scientists had then. We're talking about Joseph Banks and Cavendish, these people, who felt that engineering and science and discovery and the curiosity-led exploration of the universe were undervalued and under threat in 1799, before Faraday had even invented the electric motor and the generator. And they set up an institution called the Royal Institution in London, which is still there on Albemarle Street, whose job it was to make sure that we didn't get complacent and we continued to explore the universe. And I want you to read the first line, because I think it's something we should do politically when we're arguing for money. It's a rather more pre-Victorian, I suppose, way of looking at things. It's assertive, to say the least. It begins, and I think all our funding applications should begin like this, it begins, "It is an undoubted truth that," which leaves no room, I think, for argument. It's an undoubted truth that the successive improvements in the condition of man, from a state of ignorance and barbarism to that of the highest cultivation and refinement, are usually affected by the age of machinery in procuring the necessaries, the comforts, and the elegances of life. And the preeminence of any people in civilization is, and ought ever to be, esteemed by the state of industry and mechanical improvement among them. I think it's a beautiful piece of writing. I remind you that within 25 years, electricity in the modern world had been invented in that building. That's how I think we should start the proposal for the International Linear Collider, and I look forward to it being built. Thank you.
Thank you very much, Professor Brian Cox. You mentioned undisputed facts. It's certainly an undisputed fact. I think you'll all agree that you've given us a lot of food for thought at the speed of light there. And Einstein said that when he was trying to get his thoughts in order, he used to have a play on the violin or the piano. You're a musician as well.
Yeah, and I've never seen the connection. I get asked a lot, what is it between, physicists and scientists and mathematicians and musicians? It seems to me to be a completely different pursuit. But I'm not going to argue with Einstein. If he thinks there's some link there, I'll let him have.
Brian Foster
Maybe Brian knows, actually.
Another musician, because we'll just have a chat while the musicians come on stage, because as part of our celebrations of the completion of the technical design report of the International Linear Collider, we will have some musical delights for you in just a moment. Professor Foster, you're a violinist, and also for many years now you've been co-presenting lectures on Einstein's universe, about his love of the violin and his love of physics.
Yes, he, I think, would also agree with Brian that there's no direct connection between music and science. But what he is on record as saying is that it's a mechanism whereby the brain can relax by taking up another extremely challenging environment like music And he often found that if he was thinking about a particular problem, if he went away and played his violin or played on the piano, that somehow something would click and that would enable him to make progress. So that I think it's that idea that music is somehow an intellectual challenge of a completely different nature to science, which gives you the ability for the brain to somehow click into a different state. And I think that there is some evidence from psychologists, etc., that that's true. But I think there's also a case that if you look at Bach fugue, for example, that there are certain mathematical patterns in there which you can see and listen to as it progresses through, as things come resolve themselves. And those mathematical patterns, I think, are in a sense a scientific sort of link to certain sorts of music, but not, of course, to others.
Would you say, Brian Cox, I mean, it could be a bit crass, but, you know, Einstein was looking for harmony in the universe, and surely, you know, you were talking about, a mess of particles, or you could have a mess of musical notes that, although not all music sounds harmonious to an untrained ear, that is the attempt. There is a whole that is made out of a mass of musical notes.
I never thought about the idea that a complete musical mess was as a result of kind of symmetry breaking in a way, and somewhere beneath it there's some harmonious beauty just waiting to be unmasked. Maybe that's true. I mean, it's interesting actually, you talk about Einstein. I mean, patterns, as Brian said, probably the connection is in patterns. And I don't know, actually. I think it's interesting when you look at particle physics. I quoted Wigner very quickly. He said that there's an unreasonable effectiveness of mathematics. Another way to look at it is that we live in an ordered universe, obviously. There are human brains in it, for example. And therefore, you have to live in a patterned universe. And so in some sense, maybe we shouldn't be surprised that the mathematics that describes those patterns turns out to be beautiful. I don't know. This is philosophy, essentially. So do we live in a beautiful universe? Do we live in is the universe the only way it can be? This is one of the ideas that the linear collider and particle physics tries to answer. And there are no answers at the moment to that.
It's certainly, I think, again on record, that Einstein very strongly believed that for a theory to be correct, it had to be beautiful. And by beautiful, he meant beautiful in a certain mathematical way. It's an interesting hypothesis. There's no earthly evidence that it's true, except that general relativity is very beautiful in a mathematical way that Einstein
and the standard model
meant. And the standard model is very beautiful, as you just so nicely showed. But you can't, there's no a priori reason to believe it's to be true, except that Einstein believed it, and he was a pretty smart guy, and it turns out that the theories we have so far are all very beautiful. But, why should it be like that? We don't really know. I mean, unless you start believing that somehow the universe, as Brian said, is forced into a particular way. And there are theories which say that is indeed true, that the wonderful balance between the forces which we see, which, if they were even slightly different, would lead to a universe which was totally devoid of any interest, had no structures in it except the microwave background. Almost all universes which are possible are like that. And we live in one which has this tremendously beautiful, delicate balance, which gives rise to the enormous structures which we see around us. Nobody knows why that should be.
So it's interesting you said about possible as well. I suppose Einstein's view was that ultimately, if you really, until string theory came along, the idea of a theory of everything was that there was only one logically possible universe, which might still be the case. But it seems to be a receding goal now. The current ideas are that there are many universes with many different values of all these physical constants, engaged charges, and etc. But coupling constants, who knows?
But
we don't know.
It's quite a basic human desire to find logic to our surroundings and to who we are. I mean, you've had a very warm response, enthusiastic response to these lectures over the years. This fusion, if you like, of music and physics is something that the general public has been very open to.
Yes. Yes, that's true, and I'm not sure, I fully understand it. I mean, Brian was kind enough to come along to a festival that Jack and I run in Oxford in May, and we talked about the planets, and Brian gave a lecture on the planets, and then after that we had a performance of the planets by Katja, in fact, who was about to play on the piano. And that had a tremendous response. I mean, mostly because Brian gave a very beautiful lecture, but people stayed for the music and really very much enjoyed it. And I think it's an interesting example of that sort of synergy, that you can understand something about how people, when Holst wrote the planets, thought about science, and it's expressed in the way he wrote the music. And I think that's, again, another interesting link.
I'll just say one thing, actually, which kind of has relevance to what we've tried to do here with the public programme as well as the scientific one, is that I think I've always thought science is far too important not to be part of popular culture. And it's not had a great history of being that. Sometimes the reason that's not been the case has been the scientists themselves, because it does seem too important. It seems almost that it's self-explanatory, it's obvious. When you look at the spin-offs, you look at as we saw in the earlier talk, it's obvious that exploring the universe is a good thing to do. But it's not obvious to people unless we explain what we're doing. And I think it's only recently, actually, that we as a community, myself included, have really realised that it's a necessary part of being a scientist, is to try and explain what we're doing, because otherwise we won't be able to continue to explore the universe. And that is not a selfish thing. That means that human progress slows, and even indeed maybe goes into reverse. So I think it's very important that we keep it. CERN has made it part of popular culture. CERN is part of popular culture. It has to make sure that it stays that way, and the ILC needs to be part of popular culture as well.
Thank you very much, Professor.